So let's think about what's happening microscopically. First, let's start with no electric field. So this is just a normal chunk of metal. We again think about the ions in the metal being fairly stationary. They're not allowed to move. But we have these sea of electrons that are allowed to bounce around. The electrons are actually going pretty fast. This does depend on the temperature of the metal, but at room temperature, they are going pretty fast. Now, in between ions, they're going to go in straight lines, right? But then they interact with the ion and they bounce off in a new direction and so on and so forth, bouncing around. Now note that as it does this, it isn't actually going anywhere. Its final position is really close to its initial position, even though it traveled around, and this took some amount of time. So this is like a random walk. It is moving fairly quickly, but it doesn't actually end up going anywhere in particular. So this is the situation when you don't have an electric field, and we have to now contrast this to the situation when you do have an electric field. So in this case, we have a uniform electric field, which is pointing to the left. We have our initial position here, and remember that this is an electron, and so force equals QE, and so while E is to the left, that means that force is to the right since Q is negative. So our initial position is here. And note that it's now not traveling in a straight line because you have a force. That means you have an acceleration. And so your acceleration here is to the right. So even though initially it might just be traveling, say, this way, maybe this is your V initial, it's going to accelerate to the right, which causes it to turn, right? To curve. This is two-dimensional motion. It bounces off the ion. Again, a very simple model. And again, it would be going in a straight line, but then there's acceleration to the right, so it curves. Again, in this case, after this collision, it would initially be going straight up, but it curves. After this collision, initially this direction, but a curve, and so on. So each time, it initially has some direction, but this acceleration, due to the force, due to the electric field, causes it to curve. So because of that, you get a final position that, if you notice, is pretty much this straight down in the direction of the acceleration, even though it has been bouncing around in a slightly random way. So what we say is that there's a superposition here of random motion, again due to temperature, which were those collisions, and a net displacement. And the net displacement is due to this acceleration, which is due to the force, due to the electric field. So we see that when you have this electric field, again, it's going to be in our wire, this causes our electrons to have a net motion, even though when there's no electric field, they bounce around without there being net motion. So make sure that you understand the distinction here, because that helps explain the difference in our conductor just sitting there neutral without our electrons doing anything, versus now our conductor's in an electric field and we have some net motion of those electrons. Instead of looking at trajectories, let's make some plots of velocity versus time. And in this case, note that we're looking at only the x component of velocity, right? So in our picture before, we would have had the y direction and then the x hat direction. And we said that we had an acceleration in the positive x hat direction. So as our little electron is going on some trajectory, we see that we're increasing our x component of velocity. But then it hits an ion, right? And so when it hits an ion, it is going to then go in some new direction. So what might that look like? Well, it might initially be going backwards, but then it's going to come back again. So suddenly at the collision, we have a big change, but then it starts increasing again, coming back in that positive x direction. So we see this time over and over and over again. And again, where is this acceleration coming from? Well, this is just F over m, where F is equal to QE over m, and Q in this case is the electron charge. So we are going to get this little sawtooth plot that's basically straight lines in Vx broken by places where there has been a collision. Again, this is going to create a displacement to the right because we now don't have an average velocity of 0. It's not perfectly random motion. There are these ups and downs, but it's always increasing. So we get this average velocity to the right, which is our drift velocity. So this is where we come back and we reconnect with our idea of an electron current, because even though the electrons are bouncing around, we have this drift velocity. The other thing to note here is that sometimes the time between our collisions is pretty short. Sometimes it's much longer, but there's going to be an average time, which we're going to call tau right now. This isn't a value we're going to use very much in calculations, but you're about to see it again. So that's why we're going to need to think about that. So there is some average time between collisions, and we see that our average velocity is actually working out to be that drift velocity by definition. So what can we then do? We can then come back and create this new equation. This was our electron current before, right? This was our number density of the electrons, the area, cross-sectional area of the wire, and then the drift velocity. Well, the drift velocity is now just going to be equal to that acceleration that we found, pulling our charges sideways, times the average time, right? So this is like velocity equals a times t, but this is a random process, so we need to talk about the average time between collisions. Our acceleration is simply given by the Coulomb force over the mass of the electron, and so we get to plug this in for Vd, and that had acceleration in, so we plug these in, and so we get this new equation, right? So this is the new equation for our electron current. Why do we care? We see that it is proportional to the electric field. Now, in a future video, we'll talk about where that electric field is coming from, but if you look at this, this is actually all about the wire. This number density of electrons is going to be due to the material. We then have the charge of the electron and the mass of the electron, which is just constants. These are true no matter what. And then the tau here is the average time between collisions. That's largely due to the material, though you do have things like temperature dependencies as well. And then we have the area, which is due to the specific wire. So we have this huge proportionality term, which says that for any piece of wire, all of these things in the box are going to be constant. And then as you say, increase your electric field, you increase your electron current. So we now see that electron current is directly proportional to electric field, and now we just have to understand more about where that electric field is coming from.